would be nice to be able to. I'm gonna have to use
You guys have a laser one? I'll just use it. You have a laser one? You have a cat here or something?
I don't think I think we'll get started.
I know it's the donkey car.
I think we'll get started if you guys don't mind.
Yep.
Hi, my name is Tawn, and I'll tell you a little bit about artificial neural networks. We've got a lot of experts in here, so you guys can correct me where I've gone wrong here. But I've been studying it for about 1.5 years now, and it's a really fascinating topic. So really what I hope to do today is just give you kind of an intuition how this works, some of the basic math. I'm gonna do a little bit of hand waving and point you off to some other resources. But my aim is not to put you to sleep. Try to give you a little bit of intuition. Let's see if I can get this to go. One second. So we're going to cover brief history. I think it's worth kind of knowing this is not a brand new idea. You guys may already be aware that it's actually kind of gone through, we'll talk a little bit about the ups and downs that it's had. We'll talk about what a neural network is, and actually from here on out, I'm going to understand that we know it's artificial. We're not talking about real neural networks, so I'm going to stop saying artificial and just say neural network or network for short. But we are talking about something that's not organic, so it is artificial. How do we calculate it, and what can we do with it? And I'll follow with an example of using a neural net to do character recognition, something more concrete. Why is this not? So neural nets are an old idea. Circa 1900, we kind of figured out that the brain, although continuous, was divisible into small pieces that were neurons, and the neurons kind of participated to create a more complex activity. It wasn't quite certain at that point exactly how these complex behaviors arose out of these little simple bits, but we kind of knew that what they were. And then in 1951, we had the first, I think, working prototype of, okay, let's simplify biologically what's happening, and let's see if we can reproduce some of these behaviors. And there was a lot of excitement around that, and there was a lot of hope that we were going to, create intelligence. And there was a lot of shows at the time that had robots that were talking. We were already ready for it to just happen. We were ready for the robots to start talking to us. And unfortunately, that didn't really happen. For a number of reasons, not enough compute, there's some fundamental algorithmic advances that needed to occur. The idea of the power of the neural net kind of faded, and other things were in ascendance, and kind of hibernated for around 25 years. And then in 1980, I mean, there were still researchers, but it wasn't a primary focus. In about 1990, there's a couple developments that kind of brought it back into vogue. One is a rediscovery of a back propagation algorithm, and that's a way to reduce the error and increase the strength of the neural network. Before, there were genetic and other kind of ways for modifying your network, but the back propagation was a very powerful idea for optimization. And then simultaneously, you had Yann LeCun, who developed a convolutional neural net, and that was successful. He was successful in creating a system to recognize checks, and about 10% of the U.S. use that. 10% of U.S. banks use that for check recognition. But once again, there was kind of like a big furor, okay, what is this promising us? And there was a lot of VC funding that went into companies with big promises. They couldn't deliver. It took a lot of the wind out of the sails of the funding, and interest went elsewhere. We realized we were over-promising and under-delivering. That's not a recipe for success. So where are we now? Well, I'm going to say the golden era, but really it remains to be seen whether this is yet another situation where people are getting really excited and, you know, what is going to be the true potential for all these ideas. Well, that remains to be seen. But there's some really exciting advances that occurred. Kind of a trigger was in 2012 when there's a real famous competition called ImageNet. And until then, 2012, it was the previous best was 25% error, and it's an image recognition task where you have hundreds of thousands of images, and you have to figure out, okay, I think it's 1,000 different classes of objects. You have to say what kind of an object is in the scene. And until then, they were kind of hand-rolled features, and a neural net achieved 16% error rate, which was, at that time was stunning, because we were getting like 1-2% every year improvement, and then suddenly it was, you know, almost 10% increase overnight. So that was a big inflection point for a lot of researchers. A lot of researchers who were researching hand-rolled kind of image feature decided that this is a powerful approach. And then a year later, in 2013, DeepMind produced a reinforcement learning algorithm that was able to play Atari games from pixel input. And when I saw that, I couldn't believe it. I mean, it was pretty amazing what they had achieved for that. And since then, we've had breakthroughs in speech recognition, image recognition, speech translation, robotics control, and we're just seeing the tip of medical diagnosis, but we're now, there's a lot of money, a lot of effort getting put into that. All right, so what is a neural network? It's a computational model which is inspired by simple relationships, the idea of a neuron. And the idea that these small blocks put together create something larger. So we're going to approximate a neuron as a bunch of inputs, and then some accumulation of that input until it crosses a threshold, and then it produces an output. You can kind of simulate this by pinching yourself. And as the pressure slowly builds, you can feel the inputs are linearly increasing. You can feel the pressure, and then at some point it crosses some threshold, some inflection point, and you start feeling pain. That those inputs accumulate, and then they cross some inflection point. And we'll revisit that later on when we talk about how we structure these to imitate some of these behaviors. So let's pick a kind of a toy example just to build some intuition about what we're talking about as far as how this gets calculated. So we're going to use the example of a single neuron, which is we're going to teach it how to predict housing prices. So as input, it's going to take a square footage. This is our neuron. It's going to have some multiplier, we'll call it W, and then it will multiply the input and it will produce an output. So what do we say when we're talking about learning? We're talking about an algorithm which over time changes the value of W until W begins, this formula begins to predict the output for any given input. So how do we do that? Well, first we initialize W to some random value. Then we take one example and we compute what the output would be. We adjust the weights, we figure out some error term, and then we do a weight adjustment to get it closer to our target value. And then we take another example and repeat that. That's kind of an overview. We'll do it step by step. So step one is initialize the weights. We'll use some random noise. In this case, not a great random generator. It's giving us 1. We'll take this random value, and that will be our initial value for a weight. It's a complete guess. It doesn't really matter what the initial value is, because we're going to adjust it over time. It's a stab in the dark. So we calculate the output. This is a really simple calculation. It's our input times our weight, and that's our output. Well, we told it that the output should be 100,000, but it's outputting now 1,000. So there's obviously some discrepancy. That's our error. So we figured out, okay, what this weight should be to create the desired is something close to 100. 100 times 1,000 is 100,000. But our weight is 1. So what do we do to this to get it closer? Well, we know the difference, the gradient of this error is 99. This needs to increase by 99 in order for that calculation to be true. So the question is, how much do you change the weight? You know that the weight should change by 99, but how much do you actually change it? So we'll do a little quiz. Here's three different ideas of how you might change the weight. Option A is you calculate 100%. We'll give it a fixed learning rate. You apply 100% of that change, which would be 99. Do you add 99 to your weight? Would you take 50% of that change and only move halfway? Or would you take 1% of that change? So go ahead and talk to your neighbor and come up with an idea. I'll give you a minute. A, B, or C, which one would you choose?
C.
It's
Not too fast. It's the Goldilocks.
I give you a minute because this isn't completely obvious. And in fact, it's not, part of the reason I pose it as a question is that it's still an open problem, actually. There's kind of an accepted solution. It's not a super hard problem, but, okay, so how many people think A? How many people think B? And how many people think C? Okay, well, I'll tell you, it's B is, A is not, A is an overreaction. 100% of the weight would cause you to completely react to every single example. Half of the adjustment is actually, might feel right, but in practice is still a gross overreaction. And this might feel like an underreaction at first, until you realize that what this does is it sets you up to not overreact to any single example. But this will now require that you have many examples. And each contributes a small amount, and it helps reduce the effect of outliers. So when you have a single home that's way overpriced or way underpriced, it won't throw your calculation off quite as much. So part of the intuition behind this is that we're trying to minimize our error, and we don't get to see the error slope, but we get to feel it. We get to calculate an error term, and we get to know what direction we're moving. So it depends on your. You don't really need to know exactly what this is doing, but the intuition physically is that you could think of a ball kind of rolling down a surface, and it has some momentum, and it's trying to minimize. It's trying to roll to the bottom. And here's just an example over time of how error, depending on the different surfaces, error can get reduced and kind of level out. And here's a graph of learning rate that's set too high. So if you don't get it correct, when you correct an error in your error graph looks like this, you could end up actually overshooting, and it ends up actually increasing. And this is a kind of a worst case scenario, but you don't converge at all, you actually diverge. So we're gonna repeat steps 2 to 4. Let's take another example. Here's a 1,500 square foot home that's going for 200,000. So we plug in our example again, 1,500. Now we've adjusted our weight, it's no longer 1, now it's 2. So 1,500 times 2 is 3,000. It's still off by quite a lot. We have an error term of 197,000. So this error term, we can do a gradient and we can figure out that it should change by 131, but we've decided we're gonna do 1%, that was our learning rate. It could be whatever we choose. And in fact, in practice, this can change dynamically. There's some solvers that don't do a fixed learning rate, but they do adaptive, but for now, we'll keep it fixed. And it takes this and we adjust our weight, and now the new value for the next iteration is 3.3. And I'll just do one more example to drive it home. Here's 2,000 square foot home going for 300,000, and 2,000 times 3.3, we get 6.6. Again, a large error. We take some fraction of that, which is slightly different, and then that gets folded into the weight. So is that kind of making sense? Is there any questions?
This looks like a feedback loop.
It is. Yeah, it's a feedback loop. Right. So this can take a while, basically because the values that I've chosen, well, the weight in this example, the true value of the weight is close to 100, and we're iterating very small. So there's different things you can do to change your inputs so that that happens a little bit faster. We'll talk about that in a minute. But in general, as we've set it up, this is going to take 100 more steps to converge, and it needs a lot of examples. So here's another quiz. Okay, let's say we've got 100 data points, 100 examples of square footage and price, and we feed all 100 examples to this iterative process of adjusting our weight. That's called one epoch, one visit through all of our data. Should we stop here and say, okay, the weight is as good as it's going to be? Or should we do one more pass through the data with the exact same data, but again, using the same iteration? Or C, should we continue as many times through the same data as we like? So I'll give you a minute to think about it.
Where's D?
Yeah, so that was looking for D.
All of the above.
What would you suggest? What would you suggest D should be?
Based on the error.
Error
Based
grade.
on the amount of error.
Based on the amount of error. So there's an idea. And there are techniques that basically bail out. They just bail out, basically, when it gets to some certain threshold. But,
Of course, the best thing would be to have more data, not just 100, but
it is.
2 or 4.
Ideally, but the point is that even with the same data, so the answer is C, yes, many times, because even though you're revisiting the same data, it's contributing to the solution each trip through. Even though it's seen it, because you're doing just a portion of the adjustment towards the correct weight value, even though it's seen that example before, it does contribute to see it multiple times. Not completely obvious, but once you do it, it begins to make more sense. So on aggregate, these data points contribute. Repeated exposure helps put the solution in towards the direction of more general expression for the entire distribution. So how does it generalize? How do we measure its ability to generalize? Well, we do that as we're training by taking our set and dividing it into 2 parts. We take 80% and we say our training algorithm is going to see this much of the data, and we're going to hold and reserve 20% what that's gonna allow, this 20% is gonna simulate, once we've solidified those weights and we go out into the real world, give me an idea how it's gonna perform. That's what the test set is for. So far, we've talked about only calculating one scalar weight value. So if these are our data points for square footage and cost, this is about the best you can do. You get a linear fit coming out of the origin, and that's the best you can do with the weight. So what do? We add a constant, we add a bias term, and this allows it to lift off the origin and now fit our data a little bit better. Anybody? So that's a small adjustment. The other thing we can realize is that this problem is an idealized problem, and it's a little bit too simple. Housing prices is due to there's a lot of factors that affect the price of the home. Another one obviously is the bedroom count. So how do we factor in additional factors into a neural net? So what we do is we can add another input, and now we think about these weights as existing in these edges now, not really in the node, but in these edges. And we have a different weight for each connection. And for our idealized example, you can already see that this weight in isolation will have to have something near this scale. And that weight in isolation will need to have something near that scale to be correct. But they're actually going to contribute. They're going to linearly combine. So we take the weighted sum of inputs, and then remember the bias, the B term in that graph. That shows up. We use the bias, actually, we show it like this, but it's frequently not shown. But we think about it as another edge with a weight of 1, where it's, or actually the bias is 1, but with the weight can vary. So you can see it's starting to kind of resemble a neuron model a little bit. We have multiple inputs coming in, and we have an output. But there's kind of a problem here in that the magnitude of these inputs are dramatically different. So we can do a weighted sum of inputs. We've got, we can start our algorithm all over again. We give it an initial value, we'll give it an initial weight of 1. And we can do our calculation, 2,000 times our weight, plus 2 times our weight, and that's our initial guess. Now we can calculate an error term. We can figure out what the gradient is, and then we can apply that change. So now we have multiple inputs. How do we divide that weight, the change? So the weight new is multiplied by the learning rate times the error times the gradient. So intuitively, you have this error and you have all these incoming connections, and the incoming connections are scaled by the magnitude. So you would necessarily want to correct this one more than this one. And you also correct the bias too. So a little bit of hand waving. It's really, in practice, this is all done for you in the framework. It's more just kind of necessary to understand that the weights, the error is accumulated by all the inputs. So error is divided among inputs in proportion to the gradient. So you have the weights are all adjusting. So one other problem that we see is that we've got these inputs varying quite a lot, the scale. So there's a few common strategies. You can't actually leave them different. When I talk about scale, I mean this is 1,000 times greater than this one. You can it will actually converge, it will just take a long time.
So the point is that if you decided that the change that needed to be made was 100, that makes very little difference as to the square footage, but it completely overwhelms the room count. Is that,
It can.
that's what
yes.
you're saying, as far
Yes.
as the scale issue goes?
Yes.
Okay.
So, it helps to create a more normalized error surface if you normalize your inputs. And even better than normalizing is offsetting by a standard deviation so that your inputs go from -1 to +1 for each. So to do that, you kind of have to look at your entire data set and figure out what the average is or what the extremes are, and then you figure out the multiples. And another option to handle additional inputs is to introduce more nodes. So we'll look at both of those. So there's not really a wrong answer. Some people do B, which is just normalization alone. I think it's more standard practice to do both normalization and offset. And also introducing more nodes is also standard practice. For example, just in our square footage, if we had 4 samples that were 1,000, 2,000, 3,000, 4,000 square feet, the 2,000 square foot, this would become -1, that would become +1, this would be -0.5, and that would be +0.5. So it all kind of squished, centered around 0. So this would become that, and I didn't write the calculation, but the room count would also become from -1 to +1, so 2 might be around 0.5, depending on your data set, how many rooms you have. And momentum calculations are a little bit more stable. The error surfaces that we saw before, the learning rate, descending that, becomes a little bit more stable. So here's an example of a more regular error surface, as opposed to when you have terms that are much greater. You have these kind of asymptotic valleys, and it can deal with those, but it will deal better with a more regular error surface. And this happens to be an animation of a few different optimization techniques. They have different ways for dealing with error and applying them, changing the learning rate over time and the duration.
Some of those look better than others.
They are, yeah. Some of them will converge a lot faster. Some of them kind of overshoot. So it's definitely, it's an ongoing area of research, what kind of optimization and what techniques converge faster.
And usually there's a library that just does that for you.
Yeah, when it comes to, we'll look at a little bit of code. Try to go back. We'll look at a little bit of code, but let's see if I can. What's it doing? There's my mouse. We'll look at a little bit of code, but all those names that you saw there become just like a name selection. You just say use RMS prop or use attgrad, or and then you can understand the kind of the gross behavior of what's going on, but a lot of it comes down to just empirically just trying one versus the other on your particular data set to see how well it works. So another option for handling more inputs is to add more nodes. And there's adding more nodes, we actually do both. It does a couple of things. One, it allows separation for independent versus dependence. Some, for instance, your square footage will have a certain factor on the overall price, and the room count will have a certain factor. But you can see in isolation that they work separately when you put them together. For instance, a 500 square foot home with 10 bedrooms is a cockroach hotel. So you understand that in general, room count would tend to push the price higher. Square footage would tend to push the price higher, but there would be some interaction, some threshold where too many rooms with too small space, and now you're looking for a negative weight to be picked up. And so additional nodes will add additional opportunities for those to get calculated. Making sense?
No, because the room count isn't even connected.
Yeah, so.
Doesn't make sense.
That's what I was just about to say.
I was trying to build it.
Okay.
I'm sorry, I jumped a little ahead of myself, just a little bit. So here's the contribution from the room count. I'm gonna show them in isolation and then together, because it's gonna be a lot of lines going everywhere, real quick. So we understand that the weight is on each of the edges here, but here's our contribution from the room. Here's the independent, here's the dependent. And now we're gonna combine them all together. Here's the combination of the rooms, its weight. So this one is the combination combined, and they combine. And once you do this, once you add two nodes, you're forced to add an additional node, because these two want to output two separate values. And these two separate values, you're looking for one final output. So your network needs a single node in the end for every output that you're going to get from it. These can vary. We've added only one more, but you could add 3 more, or you could add 10 more here. And it's kind of debatable how much adding more gives you, but that's another point of exploration. It's not completely solved.
So is there a separate weight on every one of these lines?
Yeah.
Is that the idea?
So
Maybe there's a positive weight on that bottom line, and then there's a negative weight on the line going up. Is that the idea here?
There could be, yeah. And then here's kind of how they would combine. So they all combine linearly. This weight, this input times this weight plus this input times this weight combined for this value. Is that kind of making sense? Lose anybody? So this is, so far we've talked about a linear arrangement. So this is kind of where we were at in the 60s. So what we figured out is that this is good enough to describe kind of linear relationships, but it's not sufficient to capture nonlinearity. So what we did is we wanted to do the smallest change possible to make this nonlinear. So what we did was we added a function. We took, okay, whatever value is coming out of this node, we're just gonna slap an arbitrary function on it. Also a point of research, also not solved. And once again, there's functions that fall in and out of favor, and you just try different ones to see what you like. Here's, so in the 60s, we used a step function. And then in the 80s and 90s, we were using sigmoid and tanh. So to force the output of that node to be, it has this if the output would be 2, then you would go up and you figure out where the intersection, and then the actual output would be this. Something that's a 1 there, that's a 0. So it would take that input and you'd get, so no matter what the output was. And that kind of non-linearity was enough to represent things that had inflections. And then in circa 2012, people started realizing that this was overkill. That actually you could do with a rectified linear unit, which we abbreviate with the name ReLU, that can approximate, that's sufficient. That just some trivial non-linearity is enough to approximate, given all the small steps that we take for all the weights, it's enough to approximate sine curve.
And that's easier to calculate.
And it's a lot easier, that's a lot faster and easier to calculate on a GPU, which is a smaller, more specialized processor.
Actually, can I make another point?
Sure.
In the previous slide. One of the issues with the sigmoid and tangent is that you get a nearly zero gradient at each of the edges. So that meant that even though you had lots of data, you would get stuck in local flat regions of your space, which the rectified linear unit gets away from.
That is an important point. I thought it was a little too advanced to introduce that, but that's exactly right. The deeper these networks get, you run into a problem called vanishing gradients, where the error term comes from the end of your network, and it has to back propagate through the network back to the inputs. And as the depth of your network increases, those terms get smaller and smaller. And so that your activation function ends up being a limiting factor to communicate those error terms back through to the source. There's different techniques that people have taken to get around that. There's architectural changes. People have done kind of bypasses and skips, and there's other techniques that people are learning, but yes. If by default, I would suggest if you're making a brand new network, try ReLU, and well, look at what people have done and try different ones, and you'll build an intuition for yourself. So remember the pinch. This is the pressure kind of accumulating and crossing some threshold. I think that kind of motivates some of these kind of non-linearities, the responses. Now, activation. So this is just kind of trying to make it a little more concrete. We talked about activation. So what are we talking about? So again, just revisiting the idea, we have two edges coming in. We have the node. We've done the linear, the weight times the input, the weight times the input. So now that's this term here. Now we just take that activation function, whatever our choice was, and then that now modulates the output here. And we do that same thing for every node. So what does that activation get us? It gives us, we can now take the output from a noisy sine and we can fit some data that could roughly approximate a sine. And in fact, a lot of people like to think of neural networks as a general function approximator. And it takes a second to, it took me a while, I heard that for a long time and I thought, okay, well, what does that mean that it's a function approximator? It means that it's a deterministic output. It means that given the same input, you will have the same output over and over. Well, what does that mean practically? That means if you're driving your car around the track and it drives off the track, if you have the image at that particular moment that it drove off the track, you can now take that neural network that made that wrong decision, and you can offline take that image and that neural net and reproduce that error. Every single time you give it that image, it will do the wrong thing. And what that allows you to do is, because it's deterministic, because it's a function, and what that allows you to do is train it against new examples, test it against your problem image until you get a different output, different outcome. And that's because if it wasn't a function approximation, if you got some noisy output each time, you couldn't do that. You couldn't take the same input and get the same output every time. But because it's deterministic, because it's a function approximator, you have that benefit. And there's ways that you can, if your output is a distribution, is a Gaussian, there's ways that you can output data which describes that distribution. You don't have to output a single value. If, for instance, right now we're saying our housing price is this, it is 100,000, it's 200,000, but you could also say it's 100,000 with a certain distribution that it might be 1 million, or it might be 10,000, depending on some other condition. So we're gonna kind of jump a little bit to amnest, which is kind of a classic hello world problem for a lot of neural network frameworks. And this, what this does is it takes the database of handwritten digits, and as your training set, 60,000 examples, and they're 28 by 28 pixels. And what this does, you can kind of see it breaks down this number 8. So each region here is some pixel here. Kind of see the 8 vaguely. So we take each of these pixels, ends up being another input. Before, in the housing price, we had 2 inputs. We had square footage and we had number of bedrooms. That would be this one and that one. Now we have 784, 28 by 28. We stretch them all out in this case. And we take every pixel, you can see there's pixel 1, there's pixel 784, this is really, really long. And we connect them to 10 output nodes. Those 10 output nodes end up being what we call one hot encoding for the class. For example, if a 0 would have 1, if this was, this node we're gonna say is class 0, if we see the handwritten digit 0 here, we'd have a 1 here and a 0 in all the rest of these. If we say this is the class for 1, we'd have a 1 here, a 0 here, and a 0 for the rest. If this was the class for 2, there would be a 1 here, 0, 0, and a 0 for the rest.
That's what you mean by one hot.
Yes. Okay. That's, I don't know where that term comes from. If it's kind of slang or what, but it's you'll hear it. So there's some example. Here's a link. Yeah, it'll be in the notes if you want to try this for yourself. I was going to pop into a console and just show you a little live example. What could go wrong? So first I'll show you nothing because it's in the wrong window. I'll show you a little bit of Python code. It's sometimes fun to see something a little concrete. I've kind of been talking in the abstract. Here, our Donkey platform uses Keras. Keras is a, I'm going to call it convenience layer over TensorFlow, just kind of doing the main grunt work of solving our neural net. But Keras does a bunch of things for us. It calculates the dimensions of our layers, and instead of having to do it manually. So it's not important to understand each line here. It's just, for example, it's just to understand that we're importing the namespaces for different functionality that we're going to use later on. This batch size, this is how many of the numbers, how many of the digits are we going to look at before we calculate an error term and adjust our weights. 128, you'll find that actually the behavior, this will, sometimes you'll be forced to make this smaller because there'll be practical limitations on your GPU. You'll have a certain amount of memory and there'll be a certain storage for your problem domain, and you'll be forced to make this small. But you would like to make this large because you would want to calculate as many, you would want to factor in as many examples as possible, but you'll find that actually lower values, mysteriously, again, an unsolved problem, it seems to be, it's not always clearly optimal to take more. So you can kind of bracket, so for something we call these hyperparameters, you can kind of bracket these high and low and get a feeling for whether it's improving or your situation is getting worse. Number of classes, 0 to 9, so there's 10 classes. Epochs, this is how many trips through our entire 60,000 data set points are we going to make. You can stop early if you want. This is just, we've just set it by default at 12. 28 by 28 is our image size. This amnest is such a popular thing that it has some convenience to automatically load load our data for us, so we don't have to write any code. What this is, we talked about that 80-20 split test train on the left. These are your images. These are images, and these are the labels for those images. And again, for our test set, the same, these are images. We're going to train against these. We're going to use those to pretend to get some intuition about how we'll perform once we go out into the wild. This is doing some reshaping. It's not entirely important that we understand. Keras has a front end for Tawn also. So this is handling different data formats. But the other thing this is doing is it's stretching out that 2D array into a long, that's what that reshape is doing. It's stretching it out into a long vector for us. This is converting, now by default an image is an integer type, and this converts it to a float. And then we're going to do some normalization. So this is they're doing normalization, they're not doing standard deviation here. That's why I said it's common practice, but here it is, an example written by the maintainer, and he didn't do that standard deviation, but some do. This is some utilities to help us turn that label, which was a 0 or 1 to 9, into a categorical one-hot encoding. Okay, now we kind of get to the creation of our neural net. So by default, you want to start a sequential as a simple feed-forward network. That's what we've been talking about until now. There are other kinds of networks, a couple of different ones. I'm not really going to try to do a survey. I'm going to try to keep it simple tonight. And we're just going to talk about sequential. But just be aware there are different other kinds. And by default, if you download it, you'll get this model right here. We haven't really talked about what a convolution is, and I'm not going to talk about it tonight unless you guys have questions. We can talk about it a little bit. But there are different approaches to creating the network, and this is a more advanced approach. This approach right here will get us to a 99.25 accuracy after 12 epochs, which is, that's pretty damn good. That's the likelihood that given some new digit that it hasn't seen before, that it'll recognize it. But we're gonna, instead, what we're gonna do is talk kind of more along the lines of what we've shown tonight, which is we're gonna take that input and we're gonna flatten it out into one long string. We're gonna create a dense layer of 128 nodes. So each of those 128 nodes are connected to the 784 inputs. And we have a single dense layer for the output, which is 10. There's 10 outputs. You can see how we've just, we have those functions, and we just kind of list them by name here. Here's the activation, ReLU. This activation function is a little bit different. This softmax just creates a probability distribution out of the output from one hot encoding. So this line is kind of allows us to specify a loss function and an optimizer. Remember we saw that graph with those different kind of optimizers, the animation part, where those are, you can indicate those by name. Beta delta was one of those. And then we can specify what calculation do we want to make against our data to give us some idea of whether we're doing good or not.